are co-sponsored by the Department of Civil and Environmental Engineering of the USF and also the Center for Urban Transportation Research. And also this is co-sponsored by several University of Transportation Centers, including the CTEC, the Center for Transportation, Environment, and Community Health, and NISA, the National Institute of Congestion Relief, and also the TOMIT, I think, applying new tricks to old techniques. And also this seminar series are also sponsored by the student IT chapters and WTS, right? So today we are very happy to have Dr. Michael Alwani from the FAMU and the FSU College of Engineering to give us a talk about his research on the multi-scale characterization of the long-term aging of the asphalt pavement materials. And let me give you a brief introduction about Dr. Alwani. So Dr. Alwani is currently an assistant professor in the FAMU FSU College of Engineering. So before he joining the FSU, he was lab manager, I think, for the asphalt binder and the mixture labs at the Federal Highway Administration, Turner Fairbank Highway Research Center. And then I think before that, he was project manager for research projects at the Western Research Institute for 3 years. And Dr. Alwani got his PhD degree from NCSU, North Carolina State University, with I think his research topic on the multi-scale characterization of the asphalt materials. And he was a principal investigator for NCHRP research project, and also for project manager for like a USDOT small business innovation project, and also PI or principal manager for, I think, for research, like an industrial research consortium. And so far he has published over 20 journal papers and 30 conference papers, and also 7 research reports. And with that, without further ado, let's welcome Dr. Alwani for his talk. Dr. Alwani.
Thank you so much, Dr. Lu. Can you hear me now? So thanks everyone for your time, for coming here for this seminar. I'm Michael Wardani. I work for 2 universities, so FAMU and FSU. There are 2 state universities in the same city, so they decided to have one College of Engineering, and they just celebrated the 40th year of their establishment. And I'm also working as part of RIDER Center. It's the Resilient Infrastructure and Disaster Response Center. We have multidisciplinary research from social sciences, climate sciences, different disciplines related to coastal engineering, pavement engineering, and wind tunnels, everything you can imagine. Almost the whole civil engineering department with other departments and schools are doing this RIDER research. And my topic today is going to be on multi-scale characterization of and modeling of long-term aging of asphalt pavements. So if you are outside of this field, I want to tell you something, that asphalt is made out of organic materials, right? So it reacts with oxygen, get oxidized exactly like steel. And when it gets oxidized, it becomes more brittle and stiffer, and then more prone to cracking and other surface distresses. So that's why long-term aging is a very, very important topic that we have to think about. We have to model, we have to design our materials to be resistant of this thing. And of course, when you think about climate change and all these things, temperatures are going to change, and that would affect the performance of these pavements. So that's why the topic is also linked to climate change, linked to resiliency, and linked to a lot of other topics that you can think about. And the other thing is that asphalt, like 94% of paved roads are made out of asphalt. That's why asphalt is really important for our economy, for our sustainability, and so on. So that's kind of like an introduction to know about our field better. And my job is today is to try to share with you how exciting is our field, what are the cool stuff that we can do in our field, and hopefully this will, give you some idea. You will see a lot of things that we do in our field that may resonate with what you're doing in your research. So hopefully this will be an interesting discussion for you. So I want to give an acknowledgement to my previous institute. So I worked at NC State. I'm going to show slides from different institutes. So NC State, Western Research Institute. If you are familiar with asphalt binder and mixture specifications, the Sharp Super Pave specifications, one of the biggest contracts were led by Western Research Institute. So actually the current specifications that we apply worldwide, actually part of it comes from the Western Research Institute. And they have it's one of the best research centers for asphalt chemistry. And then I went to Federal Highway Administration. We were doing research over there, again, on the binder, the mixture, and other scales. So we did a lot of multi-scale work, and now I'm at those two universities. The outline, so I have a formal outline. I don't really care about finishing everything. I want to hopefully get some questions from you, have this discussion. So I'm going to talk about the bigger picture without getting into details, because I know some people are from different disciplines, okay? So I'm going to talk about how we may study the same material at different scales. And then I'm going to use the long-term aging as one example of how the chemistry, how changes on the molecular level can affect the full-scale performance of the field. So that's the main idea. This change in chemistry could happen with aging, as the example here, could happen with adding a polymer, adding recycled plastic. We recycle plastic in pavements, we recycle rubber, ground tire rubber in pavements. So any change on the chemistry on the molecular level, how it's going to affect the different scales of the material, how can we model this, and how can we predict the pavement performance at the end, and at the full scale facility. So that's the main idea of what we're trying to do here. I'm going to talk about binder chemomechanics. Chemomechanics means how the chemistry changes the mechanics of the material. Binder failure properties. I'm going to give a note about this in a little bit. Mastics and mortars. So mastics is basically if you take the binder, the liquid, and you add fillers passing from 200, say 200, you get the very fine fillers. That is called mastic. If you add the fine aggregate, then it's called mortar, or fine aggregate matrix, or fine aggregate mortar. And then if you add the whole aggregate gradation, then it's the full scale mixture. And for mixtures, I'm going to touch a little bit about viscoelastic continuum damage mechanics. Some people here are familiar with fracture mechanics. So we have fracture mechanics, continuum damage mechanics. I'm going to briefly discuss the difference between them. And then we take all this all the way to pavement structure analysis and modeling, all the way to full-scale testing facility. So we build full-scale pavements and we load it, we see the performance. So as I said, sometimes we say from the molecule to the mile, like going all the way from very small changes to the large changes. And then I'm going to talk about one step further of how something we need to do in the lab. So we wanted to develop an aging procedure in the lab. We came up with a method and a temperature to test to do this simulation. But the main idea here is the main challenge was how to link what we're doing in the lab with the climate in the field and how to try to make this really work together. So I'm going to touch a little bit about that. But again, that's like another scale where if you want to talk about climate change and stuff like that, you can feed this information into here and it's going to affect the multi-scale changes, as you can see. So I'm talking about scale in terms of material scales, but also scale in terms of time, because when we talk about climate change, we're talking about 100 years, 20 to 100 years, and we're talking about pavement performance, it's smaller than this. So long-term aging, as I mentioned, heat, oxygen would cause a chemical reaction that can change the properties of the material and cause damage. These are the scales that we have. So we have the nanoscale on the molecular level, have a microscale, mesoscale, which is in between, and then the macro scale, and then the full scale. And you can see it starts from the nanoscale here all the way to 1,000 meter, which is a 1 kilometer of the pavement. So that's going from one scale to another. On the nanoscale, we can study the material on the microscopy level. We have spectroscopy tools, chromatography tools, so more about chemistry. This is the chemistry of aging. So some of the molecular configurations here already exist in the binder, and some of them only start to formulate with aging. So you see the C double bond O and the S double bond O. That's called sulfoxide and carbonyl groups. So you see this is the change on the molecular level. And we can see this change. We have another component. So in the field, this is what happens. In the lab, because we use higher temperature, sulfoxide may further react and become sulfone, and that we don't see this in the field. We only see it in the lab. So that there are some details here. And then we take this from the molecular level to what happened on the nanoscale or using the atomic force microscopy, AFM. And you can see the changes in the binder after aging. We study this, we use machine learning, we use digital image coloration, and we try to see how we can quantify the changes in the binder microstructure and phase behavior due to the aging that happens on the molecular level. And then we look at, for example, here, an example of a spectroscopy technique. We use FTIR, Fourier transform infrared spectroscopy. And for this one, we can really quantify these are two replicates, by the way, so data is repeatable. You can look at the carbonyl peaks, so C double bond O. They have different formations, different acids and carbonyl components, but we can detect it here with FTIR. We can look at the sulfoxide peaks here with an increase in the peak here and the peak here. We can track aging. And then we normalize this data to a peak that is not affected by aging. So you can really get everything on top of each other. I'm sure people from different disciplines would probably have used FTIR at some point. And then we have the toluene peak. Why do we care about this peak? This is the solvent that we use to extract the binder out of the mixture. So I want to always check this to make sure that I don't have any residues of this solvent in the material. And then we have sulfone peaks. If the temperature was not correct or whatever, we can detect further reaction of sulfoxide to sulfone. So we look at carbonyl and sulfoxide, and this is the parameter that we use on the chemistry level to track aging. Another tool we use is chromatography. So we look at the different components of the binder. The binder liquid looks like a black sticky material, but if you look at the components, you can get a powder out of it, which is the black substance called asphaltenes, and then you get three different oil-like materials out of it: saturates, aromatics, and resin. And these four components together form the colloidal structure of asphalt or bitumen. Then we can look at them. You can see this is a more advanced technique at WRI, developed by WRI. They have about like 8 different patents on this thing. And they can even study saturates like into different types of aromatics, resins, and 3 different types of asphaltenes. So they can actually dissect the material even more. And you can see with aging aromatics component, this aromatic oil would actually turn to black powder. That's the change that we see in the material on the chemistry level by using chromatography. And then, of course, this is the colloidal stability, where we study how any colloidal structure, any emulsion you have, you need to study how stable is this material. And by taking more aromatics with aging, turning it to toluene, what happens is that your colloidal stability decreases. So the material is, it will give you problems with storage stability, with polymer modification, with all these things would be more challenging. So all of that was on the nanoscale. Now I'm going to show you one slide on thermomechanics. So this is the slide. It's pretty hard to read, right? We use machine learning. So we worked with MIT. We tried to use machine learning, and not only machine learning, because we wanted to understand what's really happening. We don't just machine learning will give you the final answer, but we wanted to really see what's going on. So we did also other correlation techniques to study the correlation between different parameters. And the main idea here is that we were able to link certain parameters we get from GPC, SEC on the microstructure level of the material using elemental analysis, SARA-AD, and OX13 determinator. So these are information. This is an information on the microstructure of the material. This is chemical information. And we were able to link that to thermal properties, rheological properties, all the way to get a black space curve, for example, from for the material. So this is the rheology or the thermomechanical property of the material. We can trace it back to the chemical and the microstructural components of the material. And if you look in this spaghetti model, you can see those red and green arrows. Green means it's a direct relationship. Red means it's indirect. And as you see, the line is thicker. That means it's a stronger correlation. If it's thinner, it's a weaker correlation, and so on. So we can really dissect this material and try to understand how the changes on the molecular level can change the binder property on the other scale. Going back to the rheology of the material. So that was the last part of this map, right? So what is rheology? Rheology is the science of the flow of the material. If you have any liquid and this liquid is flowing over time, you can really study the flow of this material using rheology. And some very well-known rheologists, they say every material is a liquid. Even if you look at it and it looks like a solid, if you give it enough time could be thousands of years, eventually it's going to flow like a material. So one example for that is glass. They found that the glass in the windows of old churches, like 100 years old, they are actually thicker at the bottom, much thinner at the top. That's because it's flowing over time. Yes, it took 100 years to do this, but it's some sort of flow over time, or creep, if you will. So rheology of the material. Rheology means that if you test the material at different temperatures and different loading rates, but I'm going to focus on the temperature now, it may behave like viscous fluid, like honey, or it may behave like a solid rubber or elastic rubber. And this really depends on the temperature. So at high temperature, it's more like a honey. At low temperature, it's more like a rubber. Same thing, it's not just about the temperature, it's also about the rate of loading. So this is a non-Newtonian fluid. If you hit it very hard, very quickly, it will behave like a rubber, as if you just hit a rubber. But if you put your hand for a longer time, it will just get inside the liquid. So it will behave more like a liquid. Whether it behaves like a rubber or a liquid really depends on the rate of loading, how fast you load this material. And that's why we call this material that it's a material that has a memory, because it remembers the response is not just depending on the rate, the way you load it right now. It's about the history of loading. What happened to this material over time? So that's why when you hear about memory foam, it's because this material has memory and can give you different response depending on the rate of loading and the history of loading. And then there is, between the rate of loading and the temperature, there is something called time temperature superposition. And by the way, you can apply this in polymer science. You study this with different materials, material science. This is basically material science. It has nothing to do with pavement. But as you can see, asphalt is a viscoelastic material, and that's why we study. So just imagine that you have a can of asphalt, and you put this can at 60 degrees C and at 25 degrees C. Of course, the flow from the can of the binder is going to be much less at 25 than if you try to keep it to flow at 60 degrees C. It will flow more, or it will, leave the container and get out like this. So the flow is more at higher temperature. However, if you leave this can for longer time, not just at 1 hour, if you leave it for longer time, eventually it will continue to flow until the response would be equivalent to this one. So for example, if you leave it for 10 hours, you will get the same response of the material at lower temperature, but using longer duration, right? So that's called time temperature superposition. It's the idea that the time and the temperature are kind of related. So we take the binder. So now we moved from the nanoscale to the microscale. This is the binder, the liquid component. And then we look at the bulk property of the material in DSR. We look at dynamic shear modulus. We look at it at different reduced frequencies. So reduced frequency here means both frequency and temperature. So both of them. We combine temperature and frequency using time temperature superposition, and we use the term called reduced frequency to study the material. And as you can see with aging, the material gets stiffer, especially at lower rates of loading or high temperatures. So this is the aging effect of the material at different aging levels. Now, the other thing is that we don't just use rheometry and calorimetry to study the material property. We can also use viscoelastic continuum damage. We can use fracture mechanics, all these things. And this is actually a big research need or research gap in our field right now. Sometimes I say this, that asphalt may be the only material that we use as engineers without breaking it apart. We still use it for design and stuff like that. We study the response in the linear viscoelastic region without breaking it all the way to failure. And that's a gap in our field. If you study concrete or anything like this, you have to take the concrete block and break it apart, or the cylinder. Or if you have a material, metal, you have to break it, timber, same thing, right? Asphalt, we don't do this, especially on the binder level. We just study the properties at the linear region and try to use it for design and formulation and modeling. So it's a gap in our field. However, we did a lot of research recently to try to overcome this gap. Then we take it one step further. So binder, if we add mineral filler to it, you can see on the left-hand side, these are the binders at different aging levels. And this is the mastic at different aging levels. And you can see how the change on the molecular level, again, remember this, the binder changes are due to aging are on the molecular level. And this is changing the binder properties. And if you add the mineral filler to it, it's going to change in a different way. So we can build models to try to see how the material is changing at the different scales due to aging. Then we can take it one step further. Remember now, see, we're using almost the same instrument, but you can see the change now from here to here. So now we've started to use larger aggregates called fine aggregate matrix. So the fine aggregate, the mineral filler, the binder, and once we add the fine aggregate, then air void is a function of the material. So air voids as well. And we try to see how the change on the binder and the mastic levels affect the change on the FAM or the fine aggregate matrix level. And you can see those are different FAM samples at different aging levels. Again, stiffer material due to aging. And the difference between the left-hand side and the right-hand side is the air void. This is 4.5% air void. This is 7.5% air void, and so on. So one thing important when you do testing and multi-scale characterization and modeling, you have to think about the properties of each scale and what kind of loading rates for these scales. It's not the same as the full scale. So you have to consider all these things in your scale scaling problem. And then we take all this all the way to the full mixture scale. This is the mixture that we use in the pavement. And we can use, now we have to use stronger piece of equipment, but we can generate the same kind of data. And you can see this is short-term age, so it's not aged yet for long-term. And then we have 5 days, 11 days, 21 days of aging, and you can see how the change in the property on the mixture scale. And the beauty of understanding these things is that you can build a model, and you can now, if you build the right model, you can now predict what would happen in the full scale, depending on what happens on the chemical scale or other scale. So you don't have to go to the lab each time you run the test. That's kind of the big picture of how these things may work. Now, it's not just about the modulus of the material, it's also about the phase angle. Phase angle means that the material, when you load the material, the response will be delayed for a little bit. There is a time lag for that. Same thing in the memory foam. If you put your hand, you'll have an indentation. If you lift your hand, it's not going to disappear right away, right? It's going to take some time. That's the phase lag or the phase change that we're talking about. So this is the phase angle, and due to aging, phase angle would decrease. So it's a stiffer material, less phase angle, which means that the response is more elastic. Then now we have to stop for a second. There is something weird in this slide. Look at the frequency here. 100,000 hertz. Do you know what does this mean? 100,000 hertz. This means you need to run 100,000 cycles in 1 second. Do we have a piece of equipment that can run 100,000 cycles in 1 second? I mean, if we have this, it's going to be very expensive, right? The university can do something like this. And look at the other side. This is 1e to the minus 9. This means that you need, for 1 cycle, you need 1 billion seconds, which is 31 years. Imagine if you are a graduate student, you need to generate this data point. You need 31 years for 1 replicate, and your advisor will tell you like 3 replicates at least, right? So it's, how do we get this data? It's, you know, it's out of our physical ability to run the test, right? And that's when we start to think about the material again. Remember, I talked about time temperature superposition and how longer duration of loading would be equivalent to higher temperatures, right? So that's, now we're using the complexity of the material in our favor to try to understand the material behavior. So longer duration means higher temperature, longer loading time means lower frequency, right? Frequency equals 1 over time. So that means this is really the physical test that we run. It's only between 0.1 and 25 hertz. That's all our ability to test the material. But then we test the material at high temperature and we get softer response. This is the model. At low temperature, we get stiffer response, and in between, we get the reference temperature. This is the temperature where we want to build the master curve. And then we say, okay, here we said that higher temperature means lower frequency. So the higher temperature here could be shifted to the lower frequency. Low temperature could be shifted to the higher frequency. And that's how we study the material over a wide range of frequencies, not by physical testing, but by using also modeling. So that's why modeling can give you a very nice capability of studying the material. For fracture mechanics, you know, people can either use fracture mechanics or continuum damage mechanics. The main difference between them is that in fracture mechanics, you have a crack. You're trying to study how the crack may propagate through your material. And you're trying to study like the crack tip, what happens in the cohesive zone, and how the crack is going to propagate and so on. And this may apply very well for macro cracks. In continuum damage mechanics, we do something else. We deal with the material as a continuum. So we say, okay, I don't care about each crack. I don't care what happens at the crack tip for each crack. I'm going to deal with the material as a whole thing and say, okay, instead of the material has the initial modulus, it's going to have a reduced modulus. But I'm going to deal with the material as a whole thing. And this might be more relevant to micro cracks instead of macro cracks. So you may start, if you want to do a very comprehensive modeling, you may start with this and then jump to this, or, you know, it depends on what kind of model you're trying to do. And there are test methods to do each one. I'll give you an example of damage mechanics or continuum damage mechanics. We get something called damage characteristic curve. It's very interesting because this is the change in the stiffness of the material. One means that you have the same stiffness of the material, the original material. So this means no damage. That's one. And then as the damage increases, this is the damage parameter, internal state parameter. and you're studying how much the modulus decrease with the increase of damage in your material. This curve is like your fingerprint. This is the fingerprint of the material. It's material dependent. And the beauty of this curve is that you can see all of them fall on the same curve. They were tested at strain control versus stress control, higher temperature, lower temperature, because we can shift them with time temperature superposition. You can do this with crosshead controlled or on specimen controlled. Any test method, load the material, no matter how you load the material, you will always get the same response if you do your math and your testing. So that's why we call it characteristic curve. Then we need something called failure criteria, where we define when the material is going to fail. And here means the inflection point here for modulus and the sudden drop in the phase angle. Why phase angle drops at failure? Because the void that is created by the crack is elastic, right? Because you load it, you get the response right away. So that means there is no time lag for the crack itself. That's why there is a sudden drop in the phase angle. So again, we study back to aging. We get different damage characteristic curves due to aging. And then we get different failure criteria due to aging. Eventually, you get all these four pieces of information: modulus, phase angle, damage characteristic curve, failure criteria. You combine all these things with pavement structure, base, sub-base material properties, traffic and climate, and you get pavement simulation. So we have finite element models. This is called FlexPave. And we can study how much damage happens at the bottom of the layer before and after aging. So that's the aging. And you can see with more aging, you get more damage in the cross section because the material properties have changed. You can see also you get much more damage at the top. So some of the cracks start from the top, goes down, and some other cracks would go from the bottom. Then we take all this, we actually run actual test, full-scale test facility. This is the facility we have at Federal Highway in Washington, D.C., in McLean, Virginia. And you can see we can compare these test results with our simulations to make sure that we get a good correlation. And we can study this also with aging and so on. So this is kind of the main part I wanted to discuss with you all. I just, don't worry about all the details and stuff. This is maybe for these folks who are asphalt people, but it's for everyone. You can just see how the material can change from one scale to another and so on. So I prefer to take a second here. Let's just, take my breath. If you have questions, please ask questions. I would like to take like a question or two before I jump into something else.
I've been driving a long time. Especially on FDOT highways. Wonder why some pavements never turn white after being brushed with paint. Well, is that done intentionally by the FDOT, or they choose which ones are the ones that don't age, are the ones that people oxidize and turn white?
You're saying that the pavement looks like black and nice at the beginning, and then it turns to white. Yeah, that could be. I mean, it is also related to friction of the tire and how you may lose some of the binder cover at the top of the aggregate that coats the aggregate surface. So over time you may lose some of this binder film at the top, and that's why the color would get back to like whiter color a little bit.
Well, I'm talking about ones that just stay black.
Oh, it would be black all the way, like throughout the lifespan. Okay.
Yeah, the FDOT engineers do that intentionally, and then choose another pavement for some stretches that is white.
So you're wondering why they keep their color black?
Yeah.
Is that what you're asking?
Yes.
One thing you may consider is that the black color of asphalt gives you a good contrast with the pavement marking. So you actually can see better the lanes and stuff in bad road conditions and stuff. It's black because asphalt is black. That's mainly the point. However, there is a research, if that's what you're trying to say also, is that in some urban development theories, they want to have lower temperatures and, having too many pavements paved with black color, they attract more sunlight and they heat, like they can make a significant urban, increase in temperature in urban areas. So there is some research to try to coat the pavement with some color that would reflect the sunlight and also more brighter colors. And in this case, you would actually get, you can decrease the temperature in the downtown of a big city or something. So that is something that there is some research and some material you can do for this. But in general, for us, it's the other way around. If the pavement is black and we keep it black most of the time, that means we actually, like, there is no loss of the coat, unless you're talking about something like bleeding. We have some other type of failure called bleeding, where the asphalt would flush to the surface at high temperature, and that would actually make it more black. And the bad thing about this is that you lose skid resistance. So cars may not, you may have accidents and say, yeah. You may have like safety issues and traffic fatalities and stuff. I don't know if Dr. Liu wants to comment on this.
I'm sure which payment section you're talking about. Probably the one that you speak with them. I'm not quite sure which payment section you're talking about, but I guess when the asphalt pavement is open to traffic, and mainly the surface asphalt film on the aggregate particle will be worn off by the traffic. So eventually will expose the color of the aggregates. So if it's the dark pavement surface after a few years of in-surface, then probably the aggregates they put in the pavement have like a dark color. And or maybe another thing, I'm not quite sure the details. So another case is that during pavement rehabilitation, like milling and resurfacing, sometimes they put a layer of the Bonco before they place the final overlay on the pavement. So probably that's the color you see, that the Bonco is like an asphalt emulsion. Maybe that's the color you see. So that's what my thought.
And actually, this quote of like adding more asphalt at the surface would actually decrease the oxidation that we're talking about. Like long-term aging would decrease because you're adding fresh material and you're blocking air from getting inside of the pavement. So less aging. Yes, it's a very good question. So one thing I wanted to share with you here, the next part of the discussion here, is that what is missing in this slide? So I showed you how this whole thing work out and stuff, but the problem is we don't know. We aged this material to 5 days, 11 days, 21 days in the lab, right? How is this related to the field? And if you are trying to simulate a pavement section in Florida versus another pavement section in Montana or in Wyoming, do you think you would get the same kind? Like, should we use the same aging protocol in the lab to simulate these pavements? No, right? And we need to think about, so what 5 days represent? Does it represent a pavement in Florida, in Texas, or in New Hampshire? Does it represent a pavement after 10 years or after 20 years? Is it the surface of the pavement where aging is much faster, or deep into the pavement section, right? So we need to link all these things, and all this data needs to be fed back into the pavement simulation. If you are simulating 20 years of the pavement life, you need to feed the data, hourly data of the climate in this location. You need to update the material property, because the material property is changing because of aging. And when the material property changes, the stress and strain response of the pavement system would change because the material has changed. So you can see this is a very complicated problem. And the problem is if you're trying to update the material property and the pavement response too frequently, then the model is going to be very hard to operate. And if you're doing some coding, you'll understand what I'm saying. You need a supercomputer to run such a model, right? So the question here is how to link all these things to field aging, how to link your lab aging protocol to field. And also here, when we did this demonstration, we used the material property. If we are doing simulation for 20 years, we use the same material property from year 0 to year 20, either the unaged property or the aged property to do this demonstration. In reality, the property of the material is going to change every year, right? So this was FlexPave version 1, and now the version 2.0 is going to be released, and that new version will have the change in the properties of the material over time due to aging. This was based on part of it is based on my PhD work. So for aging laboratory procedure, we came up with, so we compared whether we should age the loose mix or the compacted specimen. We compared whether we should use oven aging or PAV, should we use ozone or other catalysts to expedite aging. And we came up with this loose mix oven aging. We compared different temperatures, and for very good scientific reasons, we decided to go with 95 degrees C, because above this temperature, you may change the reaction kinetics, and you don't want that because you want to simulate what happens in the field. And then I'm going to just focus on duration for now. So again, the theme I'm trying to show you is how the changes on the molecular level affect the performance again. So we use some chemistry to do that. That's the kinetics modeling. So what we did in this study, it's a national study. We collected materials from all these different states. And when we collected this material, we went to field sections that are 20 years old, for example. And we were able to get the field cores from the field. We were able to also get the component materials, the original component materials that they used 20 years ago to build this road. And that's because we have something very good here in the US, something called Material Reference Library, where it's a library. You can go get the sections, get the original material, and do your research. It's a great tool for research. So we were able to utilize this tool. We collected this material from the US and Canada. And from these sections, we divided them to calibration, validation. We built the model with the calibration sections, and then we validate with the validation. So the idea is that we get the field cores, we slice them, because aging here at the surface would be higher than aging at the deeper layers. Then we age loose mix in the oven. We extract the binder out of the field and the lab. We run chemistry, FTIR, and rheology, DSR, and we try to see how much time do we need to age this material in the lab in order to meet the certain conditions in the field. That was the approach that we took. So for kinetics modeling, we did isothermal and non-isothermal. Basically, to build your model, you need to make sure that the model is working for non-isothermal conditions, because the field aging is not isothermal, right? The changing temperature. So this is the basic model from Texas A&M. I mean, there's a lot of chemistry here. Aging starts faster and then goes slower. And we use some chemical modeling here, kinetics modeling to study the material. This is the WRI model. And then we came up with our own model because we found that those two models are the same, just different mathematical representation. Again, if you boil everything down to mathematics, you can do a lot of nice things in the research. And then we came up with this model, which is basically the same thing, except that there's different definitions and different meaning for the parameters. The main idea is that now we have a material, we have a kinetic model that can tell us the rheology after aging from the rheology before aging, and one single parameter. So you have one variable. This is the material dependent, this is material property that you can get that will tell you how this material is going to age. And then these are the kinetics, the Arrhenius equation functions. So those are constants for any material, and we have only one variable for each material. And then you can see one thing we did is that we wanted to make sure it's a kinetics controlled aging reaction. So basically, we added different contents of binder to the material. When we add them, when we aged them, we found that they all have the same rate of aging. That means the film thickness of the binder is not a factor in this lab aging. Then we showed this is the motivation why we need to all these things, because those are 3 different binders. They have the same PG. When people in the construction and the DOTs and all these people, suppliers, when they go, they purchase the binder by the PG grade. They say, I want PG 6420. Those are not the same. You can get very different chemical properties. You can get different aging properties from the same grade, right? So that's why we need to take into account not just the PG, but actual properties of it. And you can see we tried different materials. The idea here was that if I have one variable in the equation, that means I just need one, I need to try this once, get the variable, and then I have everything, right? So we did aging at 95 degrees C. We get these points, we fit them, we get the M parameter. If I have M parameter, now I can predict how this material is going to age at any other temperature. So it's just I age it at one temperature, I get how it's going to age, and then I use the model. Again, this is really the beauty of modeling, that you can get a lot of information out of just simple testing. And then we did some validation studies and so on. We also tried non-isothermal aging, and again, we proved that this model is working for different aging conditions and temperatures. And then we went back to the kinetics modeling to think about lab and field. This is the idea here. In the lab, you use only one temperature, 95 degrees C, right? But in the field, you have different temperatures. So how do we meet those things together? And our goal is to try to match the lab aging to the field condition. So when we put the same equation, one equation here for the field, one equation here for the lab, and we put these 2 equations side by side, we found something very interesting. At the end, the goal is to match those 2 things together. The end is that you want the same product, right, in the lab and the field. And if you look at the equation here, those material dependent properties would cancel out, which means that you can come up with a closed form solution or one equation. In this equation, if you put 95 degrees C here in the temperature, if you put this hourly temperature history of a given location on the left-hand side, you can match them together and come up with a duration in the lab. And that's what we did. So we were able to come up with a map or an index and then a map that would represent aging in the field, regardless of what binder is used. So this is the development of the climatic aging index. And this is the equation by doing some simplifications in the model. We also did a depth correction factor because at the surface you have also photo-oxidation, ultraviolet from the sun. And at the bottom you have lower and lower aging because not just the temperature changes, but also the oxygen depletion as it percolates through the interconnected areas. So we came up with this data. Of course, when you deal with field data, you will get like scatter everywhere. And then when we started to divide them by depth, we found out, no, there is a relationship. Some 6 millimeter, 20 millimeter, below 20, like 50 millimeter, we can get different trends. And then as we try to do the modeling work, we found that we can actually improve this, like getting R-squared 0.7 from field data. That's good. You know, you collect data that has oil from the cars, you collect data that has damage from moisture. You have a lot of other features that have changed in the data. But the idea is that you can actually come up with days of aging from the climatic data. And this is measured data. This is not just from the simulation. This is the actually measured data. Eventually, what we did is that we came up with this map. So this map has we took all these equations and stuff. When you go talk to someone from the DOT or a supplier or a contractor and you show them equations, like, what are you talking about? You want to give them a product in hand that they can use. So we came up with this map. This map, for example, is these dots are telling you how many days you need to age the material at 95 degrees C to match field aging at a given year, at a given depth, and a given climate. So you can see 9 days here in Miami, 9 days in Hawaii is equivalent to 1 day in Alaska and so on. So you can reach to that by doing this work. And then we developed different versions, 40 years, 620, 50 depth in the pavement, 8 years, 16 years. And we came up with the AASHTO specification. It's a proposed AASHTO specification to try to match what we're doing in the lab to the field and to the modeling. So by that, thank you so much for your time. I hope this was relevant. I hope this at least tell you how many good stuff and exciting stuff we can do in our field. And I'll be happy to take any questions.